Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIUA campus. Okay, let's start with the lecture contents. In today's video, we will discuss what is causal signals and how to know that whether the system is stable or not, and whether it's invertible, and what is the effect of time invariance, how to judge that the system is time invariant or not. Let's go further. So causal signals. The causal signals are usually the non-zero only for time greater or equal to 0. It means that it starts at t is equal to 0 or later. For example, this is a causal signal. If you see, there is no output before time equal to 0. Right? It starts from time equal to 0 and continue onwards. And what is non-causal signals? Non-causal signals are non-zero for some time less than 0. Start before t is equal to 0. If you see that it is starting before time equal to 0, from here it is minus something. So this is non-causal signal. And what are anti-causal signals? Anti-causal signals are non-zero only for time less or equal to 0. It means that it goes backward in time from t is equal to 0. It means it will look like something in this way. Right? It will go in the negative direction. Start from 0 and go in the negative direction. Right? So these are three types of signal: causal, non-causal and anti-causal. So let's look at the example of these signals. For example, if you have a input signal x n minus 1, which is a delayed signal, right? It means that it is shifted towards the right. So for example, output y n equals to x n minus 1 is causal because here y n depends on the past sample only. Past, what does it mean? That it is not depending on the sample before time equal to 0, because this is a discrete case. So in this case, it is not depending on the samples before n equals to 0. So it is only depending on the depending on the past signal, not on the future sample, right? So let's take another example. To so this was a causal signal, and let's take the example of a non-causal signal. Yn equals to xn plus xn plus 1. It is non-causal because n plus 1 is a future sample. Future means that before the time starts at 0, its value exists. What is the future sample here? N plus 1 is the future sample here. It means it is n equals to minus 1. It is starting from n equals to minus 1 rather than from 0. For example, this is minus 1 and this is 0. So we have a sample already here, and the output depends on this sample which exists at the minus 1. So when output depends on the future sample, then it is non-causal. Let's see another example. Example 3, yt equals to minus infinity to t is the integration limits x star theta. Theta is a causal because the integral evaluates from minus infinity to t, which are all in the past, right? Minus infinity to t, which is the past samples, not the future samples. So these were some examples to show what are causal signals. The other category is memory and memoryless system. So a system with input x and output y is said to have memory if for any real time t naught, y t naught depends on xt for some time t equals to t naught. So memory, as its name suggests, if it is stored, some value is stored before the start of the system. For example, if you start something and there is some value inside, then it is called a system with a memory. So a system that does not have memory is said to have a memoryless system. Although simple, memoryless system is not very flexible since its current output value can't rely on past or future values of the input. A system with input and output y is said to be causal if it depends on xt for some time, as I already discussed, some time greater than t naught. If the independent variable represent time, a system must be causal in order to physically realizable. Non-causal system can be sometimes be useful in practice. However, since the independent variable need always represent time. For example, some situation the independent variable might represent position. So in this case, the anti-causal or non-causal signal will be useful. Let's discuss some examples of memory and memoryless systems. If you look at the output y of t here, it depends on x of t minus x square of t. It's memoryless. The reason is that here the yt only depends on xt. There is no terms like xt minus 1 or xt plus 1. So uh, similarly, yn equals to xn is a memoryless because it only depends on xn and there is no terms like xn minus 1 or xn plus 1. Here the example 3 discusses that the system is not memoryless because x minus 1, it means that at x uh, because the nth output depends on n minus 1th input, so it is not a memoryless. It means that there was a previously some value on which the output depends, so it is not a memoryless system. The first two examples deal with the memory less systems and the last one deals with the not memoryless system. The other important definition which we have to discuss is invertibility. So what is invertibility? A system is said to be invertible if distinct input signals, for example, there are two different input signals x1 and x2 produces distinct output signals, it means that y1 and y2. In other words, if invertible, if there exists an one-to-one mapping from the set of input signals to the set of output signals. It means that if we have a input signal, then different input signals, then output should be different, not the same. Then the system will call the invertible system. Otherwise, it's not invertible. So there are two basic rules that shows that system is invertible or not. So first, to show that a system is invertible, one has to show the inversion formula. First, you have to find the inversion of the given formula. So if you can find and there is some value, it means that their inverse exists and you can find the system is invertible. The other is that to show that the system is not invertible, one has to give a counter example. Counter example means that we have to prove that by giving two different input signal, we are getting the same output signal. So it means in this case, the system is not invertible. Let's see the examples for clarification. Okay, so invertible system. Example number one, if you see the example yt, we want to find the output equals to cos t plus 2 into x of t is invertible. So how it is invertible? Let's find the uh, inverse of that system. To show that the system is invertible, we need to find an inversion formula. This is easy because yt equals to this one. It implies that by rearranging terms, we need to take out this xt. So xt and then yt equals to cos t plus 2. So which is the inversion formula? Inversion formula means that if you put this x of t here, then you must get the yt. It means that yt input is equal to, it means that your result should be yt. So if you put here cos t, yt over cos 2t, so this will be cancelled out and you will finally get only yt. So it means that it is invertible. So you are cancelling the input, similar something like that. Note the denominator is always positive, thus the division is valid. So here division is valid, it's not giving an infinity result, so it's invertible. The other example which we have to show that for a discrete time system, the system is invertible. Similarly, the system, for example, yn is the output and xn plus yn minus 1 is the your given signal. So yn equals to this equation, right? So we have to prove that it is invertible. So prove yn equals to this one implies that by rearranging terms, so x and take out xn, So xn is equal to yn minus 1. So this yn minus 1, if you put this value here, so this one will be cancelled out, so you will get yn. So yn equals to yn. So this is inversion formula. Now let's see the example of non-invertible, not invertible, right? So the system given yt equals to x square t, you have to prove that this system is invertible or not invertible. So we have to prove here this is not invertible. To show that the system is not invertible, we construct a counter example. What is counter example? Let us consider two signals, x1 and x2. By definition, we already discussed that if we input two different signals to this system, and the output, if the output is same, then it means that the system is not invertible. But if we input two different input signals and we got two different output signals, then it means that system is invertible. So let's check that. If we have x1t is 1 and x2t is x minus 1, so these are two different input signals because x1 is not equal to x2t. So input are different. But if you put this x1t here, so it will take the square, so our output would be 1, right? If you similarly put x2t here in this equation, yt is equal to x2, so x2t value is minus 1, so minus 1 square you will get again 1. So output is, in both case output is 1. So therefore we have found a counter example such that different input gives the same output. So hence the system is not invertible, right? Let's discuss another property, bounded signals. A signal X is said to be bounded if there exists some finite positive real constant A such that, for example, you have a signal x of t and you took the modulus of this. So in result, modulus to get the positive value always. So x of t less or equal to A. So at any time t, the amplitude value, which can be positive, negative, but we will only take the positive, so it should be less or equal to some constant A. It means that example of bounded signals include the sine and cosine functions. If you see the example of sine, at every time t, any time t, if you take any time t, there is no value like infinity. So it is kind of a bounded signal. Whereas unbounded signal includes the tangent function and any non-constant polynomial function. For example, if you see the tangent function plot, you will see some graph like this one. So it goes to infinity at some time t as well. So when you put in tangent some value t, it may result in infinity. So it is type of a unbounded signal. So if you input any time, you get the finite number, so it is bounded. And if you put any time value in that type of signal, if you get the infinite result, it is called a unbounded signal. Okay, let's discuss another bounded input, bounded output stability. When the system will be bounded input, bounded output stable. A system with input x and output y is bistable if for every bounded x, y is bounded. For example, if you put any value of x at time t, it gives less than infinity, and yt is also less than infinity for all time. So to show that the system is bistable, we must show that every bounded input leads to bounded output. So we have to put every bounded input, possible bounded input values here, and we check that the output is also bounded. It means the result is system is bounded stable, bistable. So to show that a system is not bistable, we only need to find a single bounded input that leads to an unbounded output. If, for example, in the case of tan theta, if you put some value of time t, at that time if we get the any value, there can be number of values, but for example at any time t, it gives you the infinite result, so it means that that system is not bistable. In practical system, bistable system is well behaved in the sense that as long as the system input remains finite for all time, the output will also remain finite for all time. So when you get finite input, you will also get the finite output. So this is called a bistable system. Usually a system that is not bistable will have some serious safety issues. For example, we can discuss the daily life example. For example, iPod with a battery input 3.7 volt. You are inputting 3.7 volt as a battery, and headset output gives you infinite results, infinite volt. So it means that you will die, right? Because you will be vaporized, uh, Apple customer, and one big lawsuit. So there will be case on you as well. So bounded input, you if you get input give 3.7 volt and you get the desired voltage, it means that it's stable. Otherwise, it's unstable. So you will have some damage. The other important property is time invariant. What does it mean? That a system is time invariant if a time shift of the input signal results in the same time shift for the output signal. For example, if you have input xt, so at input xt you get the time, you get the output yt, right? And if you give, then the system is time invariant. When the system will be time invariant when you give the input x at t minus t naught, and in the response you get the output, same output as this one, but at the delayed time, for example t minus t naught. So when you get same output at t minus t naught, then it is called a time invariant system, right? For any time t naught which belongs to some real number. Figure shows an interpretation of the time invariant system. If signal xt is input to the time invariant system, for example, this is your time invariant system, and get an output yt, you get the output yt. Then the input xt minus t naught will result in output yt minus t naught. If here you see that it is a time invariant system, you input xt minus t naught, so the same result will not occur at yt, it will occur at yt minus t naught. So it is time invariant system. Time invariant in simple, it means that it doesn't vary with time. So it is not dependent on time, right? Okay, let's see the example of time invariance. Example 1, for example, yt equals to sine xt is time invariant. Now we have to prove that it is time invariant. How it is time invariant, right? Let us consider a time shift signal. X1 is equal to xt minus t naught. Now we shift that input to t minus t naught. So correspondingly, we have a y1t which is output x1t. Therefore, y1t equals to sine x1t. So sine xt minus t naught. If you put here xt minus t naught. Now we have to check whether y1t equals to yt minus t naught. To show that, we know that yt minus t naught equals to sine xt minus t naught. It means that if we check the calculate the value of sine theta, sine of xt minus t naught, we get the same output as y of t at sine x of t. So only the delayed version. So which is same as y1t. Therefore, system is time invariant. The other important property is the linearity of a system. When the system is called a linear system, a system is linear if it is additive and scalable. That is, if you input this is scalar, like scalable, and additive means this positive sign. So ax1 plus bx2, if you have a two types of input, ax1 plus bx2, and in result you get ay1t plus by2t. So it is additive and scalable. If you satisfy this property, right, ax1t plus bx2t gives you a1 y1t plus by2t. It means the system is linear. So this is an example to show whether the system is linear or not. For example, you have a system which has an input 2 pi xt. It is a linear. We have to prove that. So output is yt. So see this. Let's consider a signal xt. For example, we have this xt which is equal to, as we discussed previously, ax1t plus bx2t. So and we also have to find a y1t and b y2t. So let's find y1t first. So y1t here is 2 pi x1t, right? And y2t here is 2 pi x2t, right? Then add them. So by and multiply by some scalar a scalar. So a y1t, it means that a 2 pi x1t, right, this one, plus b y2t. means b into 2 pi x2t. Let's take 2 pi common here because it is common in both. So 2 pi, then it becomes ax1t plus bx2t, which you know that is equals to xt. Right here it is xt, which is ax1t plus a plus. So it is similarly as 2 pi, it can be written 2 pi xt, which is equal to yt. So both of them are equal, right? Yt, and here we also have a yt. So it means that the system is linear. Now let's check the example of non-linear system. For example, you have a system yn x2n whole square. It is not linear. To see this, let's consider an example. Uh, the signal xn, which is equal to x1n plus bx2n, similarly as we considered here. So where y1n, we have to find y1n and the y2n as well as previously we did. So y1n, put here x1 2n whole square plus y2n x2 2n whole square. Now we want to achieve see whether yn ay1n plus by2n it holds or not. So let's see ay1n. So a into x1 2n square whole square, right? And by plus by2n, which is plus bx2n whole square, right? However, if you see that yn equals to, if we open this one, yn, it is x2n whole square. If we put x2n here using this equation, right, this equation, so you will have ax1 2n plus bx2 2n, right, this one. If we put this equation in that one, you have to take whole square, right? So it becomes a square plus b square plus 2ab, which is not equal to this one. So they both are not equal. So it means that the system is non-linear. So this system is non-linear. In this way we can verify the linearity of a system. So whether the given system is linear or not. Thank you for listening. And for question answer session, there will be some reserved slot. So exact time will be communicated later on. Thank you.